So in this video lesson, we're going to have a look at velocity and speed. So we're going to start by talking about velocity. And so velocity is when we are dealing with displacement related to time. Okay, so velocity is a displacement over a period of time. Now, speed is actually distance over a period of time. So velocity and speed are very closely related to each other. The difference being that one is based off displacement and one is based off of distance. So velocity is based on displacement, speed is based on distance. So when we're looking at velocity, the symbol for velocity is a V with a little arrow over top of it. And the symbol for speed is just a V with no arrow, meaning that velocity is a vector and speed is a scalar quantity. Okay, so velocity has a direction associated with it since it's based off of displacement, which also is a vector and has a direction associated with it. Speed is a scalar since it is based on distance and so does not have a direction associated with it. Now, when we are calculating velocity, we are calculating the average velocity. Okay, there is such a thing as instantaneous velocity, and that's a velocity at any one very specific moment in time, but that is going to require calculus to solve. We're going to use average velocity, which is over a period or an interval of time, and that's going to require no calculus, and those are the types of velocity calculations that we're going to be doing. All right, so to calculate average velocity, we are going to use our change in position, which we know is displacement, and we are going to divide that by the change in time. Okay, so to calculate our average velocity, we are going to use the displacement divided by time. Okay, when we're trying to calculate speed, we're going to use the distance over the change in time. Okay, and so you see the difference between velocity and speed being that velocity is using displacement, speed is using distance. The units that we're going to measure velocity and speed in are actually both the same. We're going to measure in meters per second. So we are measuring displacement and distances in meters, and we are going to measure time in seconds. And so we're going to get a unit for velocity and speed as in meters per second. Okay. Now, don't forget, velocity will have direction and speed will have no direction. Okay, so an example of a velocity could be 40.5 meters per second to the east, and an example of speed could be just 40.5 meters per second. Speed has no speed has no direction associated with it, whereas velocity has magnitude as well as direction. Okay, so we are going to do a big practice problem that's going to involve us calculating displacement, distance, velocity, and speed. Okay, so our practice problem here. Okay, so with this practice problem, we are going to have two people. We're going to have Jill and we're going to have Jack. And Jack and Jill are siblings, of course. And they are training for a race. And so they are going to run different routes, and we're going to see who is going to win this race. All right, so Jack is going to run. First, he's going 10 kilometers west, then 8 kilometers north, and then 6 kilometers to the east. So that's Jack's route. Jill's route, she's going to go 6 kilometers to the west, 7 kilometers north, 5 kilometers east, 2 kilometers north, 3 kilometers west, and then 1 kilometer south. So Jill has a much more complicated route. Okay. Both of them are going to run this route in 2.50 hours. Okay, so for each of them to run their specific routes, it's taking them 2.50 hours. All right. The first thing that I want to actually do is convert that 2.50 hours into seconds. Whenever we're calculating velocity or speed, we want our time to be in seconds. And so that's the first little conversion that we're going to do. So we're going to do our 2.50 hours, and we're going to multiply using our conversion factors. And so we know that there are 60 minutes in 1 hour. And we also know that 1 minute is 60 seconds. And so we're going to convert that so that we can get our time in seconds. So 2.5 hours, we're going to multiply by 60 and then multiply by 60 again. So we're getting a time of 9,000 seconds. All right. So now we could draw their routes if you want. So we could draw a picture to show their routes. So let's go ahead and do that. And I think we will do that on graph. So if you have a piece of graph paper, use your piece of graph paper. I'm going to add a graph to my page here, and then we're going to draw Jack and Jill's route. All right, so I'm going to start, I think, down here, right at the bottom here. So let me start here. And I'll draw Jack's route first. So we'll put him in blue. So Jack is going 10 kilometers to the west. I'm just going to use one box to be 1 kilometer. So 1, 2, 3, 4. So he runs 10 kilometers to the west and then 8 kilometers north. 1, 2, 3, 4, 6, 7, 8. So 8 kilometers north. And then 6 kilometers to the east. 1, 2. Okay, so this is Jack's route. So he's going 10 kilometers and then 8 kilometers and then 6 kilometers. Okay, and then I'm going to draw Jill's route. So Jill is going 6 kilometers west. So 1, 2, 6 kilometers west, then 7 kilometers north. 7 kilometers north and 5 kilometers east. 5. And then 2 kilometers north. And then 3 kilometers to the west. And then 1 kilometer south. All right, so this is Jill. Hers is a bit more complicated, but they actually are both ending at the same point, okay? So then we're going to draw our displacement here in green. And what that means is that our displacement for both of them is going to be exactly the same. And so we're going to draw our little triangle here. All right, so if we're looking at this triangle for displacement, we are going 8 kilometers up on that triangle. And the triangle is 4 kilometers at the base, okay? All right, so that's our picture. So now we want to calculate each of their displacements. We're going to do each of their distances. We're going to do each of their velocities and then each of their speeds. So we're going to do all of our calculations for everything. So if we're going to start with Jack. Okay. So we're going to calculate Jack's displacement. So his displacement, we're going to use that green triangle that we drew. And we know that that's also going to be Jill's displacement. So that's nice. We're only going to have to calculate that once. So to calculate his displacement, we're going to have to use our Pythagorean theorem. C squared is going to equal to our A squared plus B squared. And so our C is going to be the square root of our 8 squared plus our 4 squared. And so let's do that. So we'll do 8 squared plus 4 squared and then square root it. And so our displacement is going to be 8.9 kilometers. Okay. And so that's going to be the same for Jill. Jill's displacement is also going to be that 8.9 kilometers. Okay, and then we're going to calculate our angle. And so the angle that we want, we're going to choose the bottom of the triangle to use that angle in. So if we look at our triangle here, this was our start at the bottom here, and at the top here was our end. And so we want this angle down at the bottom of the triangle, and that's going to give us our angle for our displacement. So we're going to use tan theta. So in this case, that's going to be our 8 kilometers over our 4 kilometers. So we're going to get an angle of 63 degrees. And so our overall displacement for both Jack and Jill is 8.9 kilometers. And we are north. Oh, nope, not north first. We are west 63 degrees north. Okay, so we're going to be west and then 63 degrees to the north. Now, if we want to do north first, then we just have to subtract that angle from our 90 degrees. And so if you wanted to, you could also say north 27 degrees west. Okay, and those two directions are equal to each other. Okay, but what we need to look at in our triangle is that when we're looking at this angle, we are first going to the west, then we are going to the north. And so that's the direction that our directions need to go in when we're giving our angle for our displacement. Okay, so both Jack and Jill have a displacement of 8.9 kilometers, and they're going in the direction west, 63 degrees to the north. Now, if we want to do our distance, so if we're looking at Jack, so Jack's distance is going to be his 10 kilometers plus his 8 kilometers plus his 6 kilometers. So Jack's going 24, not 22. So Jack's distance is 24 kilometers. And then if we do Jill's distance, so she's going 6 and 7 and 5 and 2 and 3 and 1. Oh, she also went 24 kilometers. So they traveled the same distance. They also traveled the same displacement. Okay. Now, if we want to calculate their velocity, Then we're going to use their displacement over the time it took them. And this happens to be the same for both of them because we found out that they both had the same displacement. So their average velocity, we're going to actually do this in kilometers per hour. Okay, so our displacement was 8.9 kilometers, and we were west 63 degrees north, and our time was 2.5 hours. So we're going to get an average velocity of 3.6 kilometers per hour, and we're still going in the same direction as we were our displacement. And so this is going to be our velocity. So once you have displacement figured out, velocity is a pretty easy calculation as long as you know the time for that displacement. Okay, and then if we want to calculate our speed, so to calculate our average speed, we're going to have to use our distance over our time. And so our distance traveled was 24 kilometers. Again, we traveled over 2.5 hours. And so we're getting 9.6 kilometers per hour as our speed. Okay, now when we're looking at velocity versus speed, we have the same kinds of differences as we had with displacement versus distance. Okay, speed and velocity could be equal to each other, but they don't have to be equal to each other. Speed, if it's not equal to velocity, then it will be larger than the velocity. And velocity should always be the lower of the two, unless they happen to be equal to each other. And that's because velocity is based off of displacement, and speed is based off of distance. Okay, now we are going to do another velocity problem. Only in this second velocity problem, we are going to use a different method for solving because we are not going to be able to make a beautiful right-angled triangle to solve for our displacement. Okay, so in this first practice question, we were able to make that nice right-angled triangle so we could use Pythagorean theorem and our tan theta to find our angle. In this next practice problem, we're going to have to use a new method, and this new method is going to be called vector decomposition. So this is going to be practice number 2. And this one is going to use a method called vector decomposition. Okay, so when we're looking for this method again, this is the practice problem that's going to have vector decomposition in it. All right, so in this practice problem, we're going to have an airplane, and the plane is flying 56 kilometers, and we're going west 35 degrees north, then, in 23 minutes. Okay, then we're going 34 kilometers west, and we're traveling in that direction for 22 minutes. Then we're going 78 kilometers south, 80 degrees to the east, in 1 hour. Sorry, that was supposed to be 1.00 hour. Okay, so here we are going to try and solve for the displacement of the plane. Okay, and then we're going to solve for its velocity. Okay, in this one, I'm not going to ask us to solve for the distance that the plane traveled or the speed. We're looking for the displacement and for the velocity. All right, so the first thing that I want to do is each of these directions have, each of these displacements have a direction associated with them. And so we're going to draw an axis. And so I'm going to try and draw the nicest axes I can without being able to use a ruler on my iPad. And essentially this axis is going to act as our compass rose. So we have north, east, south, and west. Okay, and we are going to draw each of these vectors, okay, because they're vectors, they have magnitude, they have direction. We're going to draw each of them onto our axes. And so I'm going to label them, and I'm going to draw them in different colors. So I'm going to call this one's going to be number 1. And then I'm going to have number 2 here in green. And then I'm going to do number 3, I think, in a purple. All right. So my first vector, we're going 56 kilometers. And we need to travel in the direction west, 35 degrees to the north. So all of my vectors are going to start at the origin. And so that's going to be my vector number 1. So that is west, 35 degrees to the north. And it is 56 kilometers in terms of its magnitude. Okay, so that's my vector number 1. Vector number 2 is 34 kilometers, and it's going directly in the direction of west. So it's going to be right on the axis here. So that's my green one here. And that is 34 kilometers. No angle associated with it because we're going directly on the axis. We're traveling directly west. Okay, and then my third vector is going to be the purple one. And that vector is south, 80 degrees to the east. So we're somewhere up here. So we've got our 80 degrees here, and that vector is 78 kilometers in magnitude. Okay, so this is called the vector decomposition method. And what we're going to do is we are going to take apart these vectors that are at weird angles. We are going to take them apart into the part that's going west or east, and the part that's going north or south. Okay, so we're going to go back to vector number 1. So that was our red one. And what we're going to do here is we are just going to attach the end of our vector to the axis, so that the vector itself is going to be the hypotenuse in 2 right-angled triangles. So we know that would be a right angle down here, and this would be a right angle down here. Okay, we're going to do the same thing with our purple vector. So that now our purple vector is the hypotenuse of those 2 right angled triangles that are identical to each other. Okay, so those 2 triangles are going to be exactly identical to each other. All right, now going back to our red vector, we don't have to do this with our green vector number 2 because it's already on an axis. It's just going west or east, right? And so it doesn't have to get decomposed, okay? All right, so what this is going to mean is that for our red vector, so this is vector number 1, we're going to call this dx1. So this is a displacement of our first vector on the x-axis. And then the vertical one is going to be dy1. So this is the displacement of our first vector on the y-axis. We're going to do the same labels for our purple vector. So we're going to have our dy3, because purple vector was the third vector. And then this will be our dx3. Okay. And so again, we're taking apart that vector into its x and y components. So how much of it is on the x-axis, how much of it is on the y-axis. So how much of it on the north-south, which is the y-axis, how much of it is on the east-west, which is the x-axis. All right. Now what we're going to do is we want to actually add up all of our vectors on the x-axis and all of our vectors on the y-axis. Okay, so I want you to remember that vector number 1 and vector number 2 we took apart, and we took them apart into dx1 and dy1 and dx3 and dy3. Okay, vector number 2 didn't get taken apart at all. Now, before we can add everything up, we need to label our axes. And with our axes, I'm going to choose north to be positive and south to be negative, okay, in terms of direction. I'm going to choose west to be positive and east to be negative, okay? The reason that I chose north is because I just had to pick north or south to be positive or negative. Doesn't matter which one you choose. East or west, I actually picked west because I have more things that are flowing in the west direction on that axis than in the east. And so I'm going to choose west to be positive. But again, if you choose the opposite, that's fine too. Just make sure you know which direction you're going to choose to be positive and which direction you're going to choose to be negative. Okay, so now we want to figure out what's going on in terms of all of our vectors on the x-axis and what's going on in terms of all of our vectors on the y-axis. Okay, so our displacement on the x-axis, we are going to add together our vectors that are on the x-axis. So we have positive dx1 because it's going in the westerly direction. Okay, we have vector 2, not the x component of vector 2, but actually vector 2. And then we have negative the x component for vector 3 because it's going in the east direction. Okay, so that's happening on our x-axis. Our y-axis, so in our y-axis, we have a positive dy1 because it's going north. We said north was positive. We have no part of vector number 2 that's on the y-axis. That's the green one. And so we have no part of vector number 2 on the y-axis, so it's not there at all. And then we're going to have a negative dy3. Okay. Oh, sorry, this was supposed to be positive dy1. So positive dy1 because it's going north, and then negative dy3 because it's going to the south. Okay, so now we have to substitute some actual numbers in there. And so when we look back at our diagram, I want you to have a look at the fact that each of those vectors that we took apart, vector number 1 and vector number 3, when we took them apart so that they would create right-angled triangles. And we have the hypotenuse as well as one of the angles in the right-angled triangle. So that means that we can find the lengths of the sides that we need. So we can start with our first vector. So our dx1, if we just look at that there, dx1 in that triangle is going to be adjacent to our 35 degrees. And so dx1 being adjacent to our 35 degrees and having the hypotenuse of 56 kilometers, we are going to use cos. So cos of 35 is going to be equal to our adjacent side divided by our 56 kilometers for my dx1. So that means that dx1 is actually 56 kilometers times cos of 35. Okay, and you might have to redraw this triangle if you can't see why dx1 is adjacent to the 35. You have to think about the fact that both of these triangles are the same. Okay, they both share the hypotenuse of 56 kilometers, and that means that our 35 degree angle would also be up here. okay? And then our complementary angle of our 65 being on the other side. Oh, not 65, 55. So then we have our 55-degree angle up here as well. Okay, and so since dx1 is 56 cos of 35, the dy1 actually becomes a lot easier to do. Once you've figured out which component is cos, because it's adjacent to your angle, then the other component has to be sine because it's got to be opposite to your angle. So that means that our dy1 is 56 sine of 35 degrees. Okay, we're going to do the same thing with our third vector. Okay, so with our third vector here, our dx3 is going to be opposite our 80 degrees, which means the dx3 is going to be sine of our 80 degrees. So dx3 is going to be 78 kilometers, which is our hypotenuse, sine of 80 degrees. And then our dxy has got to be adjacent to the 80 degrees, so it's going to be 78 cos of our 80 degrees. Okay, all right, so we can go back into our calculations for the displacement on the x-axis, the displacement on the y-axis, and so we're substituting what we found for dx1, d2, and dx3. So dx1 was 56 cos of 35. D2 was just 34 kilometers. And then we're going to subtract our dx3, which is 78 sine of 80. And so then that's just math. Okay, so our 56 cos of 35, and then we're adding 34, and then we're subtracting 78 sine of 80. It's going to give us 3.06 kilometers. Since that is positive, we know that's 3.06 kilometers to the west. So then we're going to do the same thing with our dy calculation. So with our dy1 is 56 sine of 35. And then we're subtracting dy3, which is 78 cos of 80. So we're going to do that math. 56 sine of 35 minus 78 cos of 80. And we're getting 18.6 kilometers. And since it's positive, we know that means it's going to the north. Okay. All right. So now we know we're not quite to our overall displacement yet, but pretty close. But we know that we have an overall displacement that is going 18.6 kilometers to the north, and then 3.06 kilometers to the west. You know what? Let's move this 18.6 to the other side. So that means our overall displacement is somewhere here. So we're going somewhere in the northwest direction. Okay, now we have this nice right angled triangle again. And so now we can use our Pythagorean theorem to solve for that overall displacement. So that overall displacement, we're going to use the square root of our 3.06 squared plus this 18.6 squared. So we're 3.06 squared plus 18.6 squared, and then square root. So we're 18.8 kilometers. And then we also need to calculate our angle. So tan theta, we're going to do 3.06 divided by our 18.6. So that's going to give us a theta of 9.3 degrees. And so that means that our overall displacement is 18.8 kilometers. And we are north 9.3 degrees to the west as our overall direction as well. So that's our overall displacement. Then if we want to calculate our overall velocity, we know that we just have to take our displacement divided by our total time, or our change in time. And so our displacement is 18.8 kilometers north, 9.3 degrees to the west. And our time, we're going to have to go all the way back up to the beginning of our problem here. We've got 23 minutes, 22 minutes, and 1 hour. So 23 minutes plus 22 minutes plus the 60 minutes in an hour, we're looking at a total time of 105 minutes, okay? Now, we probably want our velocity in kilometers per hour. So we're going to take our 105 minutes and just turn it into hours. So it's 1.75 hours. So we're looking at an average velocity of 10.7 kilometers per hour. We're going north 9.3 degrees to the west. Okay. All right. So this vector decomposition method is a little bit long. It takes a little while. Again, though, the reason that we're using it is because we can't actually take those three vectors and make ourselves a nice right angle triangle to add the vectors together. And so the vector decomposition method is really nice when you have vectors that are moving in weird directions. They're not perpendicular to each other. And so you can't create a nice right angle triangle out of them. It will be very clear that you need to use the vector decomposition method as soon as you have directions, you can see here, that are not at right angles to each other. Then you're going to have to use that vector decomposition method. Okay, there is a lot of practice to do with this vector decomposition method, and so make sure that you're working on those practice questions. Make sure you do the practice, and you can use this example to follow through. And the method works the same way every time. And so you can actually just follow through the same method over and over and over, and it'll work for every vector decomposition problem that you have to do. All right, so that's the end of this video lesson. This is velocity versus speed, and then using the vector decomposition method to get us displacement, which will then help us to solve